In this video, we are going to learn how to find determinants of matrices that might be the product of other matrices, or maybe the scalar multiples. Let's start with two matrices. Let A and B be n by n matrices, and let C be a scalar. Our first property says that if we want to take the determinant of C times the matrix A, then the resulting determinant is C to the n power times the determinant of the matrix A. So something that you want to make sure you notice is that the exponent n is the same n that comes from the size of our matrices, the n by n matrices. And another thing that you should notice is that this is not the same way that absolute values work, even though we use the same kind of notation, this vertical bar notation, as absolute values. Because if this were an absolute value, this scalar would also have an absolute value on it. But if C is negative, then you have to pull the minus sign out with the C. The second property tells us how to take the determinant of the product of two matrices, and to do that, we just take the product of the two determinants. So essentially, the determinant distributes over multiplication. Next, we'll discuss transposes. If we take the determinant of the transpose of A, then nothing changes. It's the same as the determinant of A. To take the determinant of the inverse of a matrix, we do 1 over the old determinant. Of course, we have to assume that the inverse of A actually exists in order for this to make any sense. Now let's use this theorem. We're going to have a 4 by 4 matrix called A, and the determinant of A is going to be minus 5. And what I want to do here is take the determinant of 3 times A inverse. So let's work through how to do this. The first thing we should deal with is the scalar 3. And in order to pull that outside of this determinant, we have to think back to the size of our matrix A, and also the first property from the theorem. So this property tells me that I can pull 3 to the front, but I have to put an exponent on it. And the exponent should be the same as the size of the matrix. Here's a 4 by 4, so the exponent is 4. Now we've pulled out the scalar, and we have to deal with the inverse. So for this one, we go up to property 4 of the theorem, which tells us that the determinant of an inverse is 1 over the determinant of the original matrix. So now we can just plug in this determinant, since we already know it, and we get 3 to the 4th power over minus 5. This theorem also helps us answer more theoretical kinds of questions, like in this example. Let's suppose that A and B are n by n matrices, and also suppose that B is singular. You might have to think back to the previous video where we learned the definition of singular. This means that the determinant of B is equal to 0. And here's the question we want to answer. Is A times B singular? So is the determinant of A times B equal to 0? In order to answer this, we use the theorem, and we're actually going to use property 2, which tells us that to take the determinant of the product of two matrices, we just multiply the two determinants. And we already know the determinant of B, since B is singular. We know that it's going to be 0. So we can plug in 0. And no matter what we get for the determinant of A, which we don't actually know in this example, when we multiply it by 0, we're going to get 0. So that means the determinant of A times B is actually equal to 0, which means that A times B, is singular.